Today's show is brought to you in part by support from Science Sandbox, an initiative of the Simons Foundation. In appreciation of our guests' participation, we have made a contribution to the following organization on their behalf.
The John Egging Trust, helping young people facing adversity to be the best they can be. For more information, please visit johneggingtrust.org.uk.
You could think of atoms of space and time in some sense. We have no idea what they are, but the strong suggestion seems to be that there are such things as building blocks of space and time. What that means for the passage of time, what time is, it's not really well understood at the moment by any stretch of the imagination. But I think it's interesting that we are beginning to glimpse something. Einstein had a beautiful quote. He said, "Something deeply hidden."
Welcome to Sing for Science, the show where musicians and scientists talk about music and science. I'm your host, Matt White. Each week, we'll talk about a song by our guest artist and how it connects with our guest scientist's area of expertise. Today, we'll be speaking with Nick Rhodes, synth pioneer and co-founder of the legendary band Duran Duran. Duran Duran formed in Birmingham, England in 1978 and went on to lead the second British invasion and the MTV age with their high-concept videos and massive international success. Nick's synthesizer prowess is featured prominently in their 1982 hit Save a Prayer, helping define it as one of the most popular songs in the band's catalog. Also joining us today is particle physicist Brian Cox. Brian is a professor at the University of Manchester and is perhaps best known to the public as television host for the Wonders of and Stargazing Live series on the BBC. We are fortunate to have Brian with us today as he is regarded as one of the world's best science communicators and was made a Royal Society Fellow in 2016, the UK's most prestigious distinction awarded in the sciences. The title of this week's episode on the podcast is Save a Prayer, the God Particle According to Modern Physics. Hello, Nick and Brian. Thanks so much for coming on the show.
Hello. Thanks for having us.
Yeah, pleasure.
Nick, Save a Prayer has one of the most iconic sounding instrumental hooks of any pop song. And I'm talking about the jumpy flute sounding phrase that repeats throughout the dun, 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 dun. Could I ask you to describe to our listeners what that sound is and how you perform it?
Yes, it was made with a Roland Jupiter 8 synthesizer. It's a very simple sound. I took one of the patches on there and just tweaked it a little bit to make the sort of stringy sound. It's like a cross between a string and a flute, I suppose. And it's just using the pitch bend to literally wobble the note, change the note. And it's an incredibly simple part. But then I've always found that the simplest things are usually the most effective. The way that song came about was that I had a new gadget, a Roland Space Echo, and I wanted to figure out how it worked. And I'm not very good at reading instruction manuals. So I just dived right in. On another synthesizer, I played what became the sequencer. I didn't even think about it. I just played a few notes and let it go round in a sequence so that I could feed them into the echo chamber. And then I could find out how to get the echoes in sync with the sequencer, which is the effect you hear. And then when I did that, after listening to it for about 30 minutes while I was figuring out how to work the echo machine, I suddenly heard a melody in my head, which was the melody of Save a Prayer. So I went on to the Jupiter 8 and found it. And I don't know why I was hearing the wobble in it, but because usually it's the first thing I'd ever played and used the pitch bend in that style. But then I was playing that on top of the sequencer. And at that point, the rest of the band arrived and said, that's not bad. Let's try and make something out of that.
Wow. And that pitch wobble, that resembles a joystick in appearance,
Yes,
kind of, right? A video game.
yes.
I think it requires quite the deft touch. I mean, maybe not bebop on a trombone, but let's
Uh,
be honest.
yeah,
That's
no, I'm definitely more Coltrane than bebop on a trombone, I think. But yes, I mean you've got to, of course, set it to the right levels. But there is a way of cheating with synthesizers in that you can set the sensitivity of the pitch bend. So if you want it to bend by 1/5 or a third, you can set
okay.
that. So if you bend it all the way to the end of the available space, then you can actually get it right.
Okay. Well, thanks for letting us in on that. You know, there's one thing that has always mystified me. Simon has described the chorus of that song as based on Gordon Lightfoot's "If You Could Read My Mind," and it's not every day you hear Duran Duran and Gordon Lightfoot mentioned alongside one another.
No, I don't know. That must be something that inspired him for the melody somewhere. He
Yeah.
has bizarre and obscure taste, Simon. It can be anything from Chopin to obscure choral music to new electronic music or David Bowie and Lou Reed. Gordon
Mm-hmm.
Lightfoot, I don't know where he fits into that spectrum.
Yeah.
I really
I
don't.
don't know that. I don't know that I hear it. So, quick footnote question: this period that we're talking about in the early '80s, you have "Hungry Like the Wolf," you have "Rio" on the charts, "Save a Prayer." I think it's fair to describe the hysteria surrounding Duran Duran's public appearances as not unlike Beatlemania, where you're trapped inside places, surrounded by mobs of fans. And I've always wanted to know, were those situations terrifying, or did it feel like it was harmless, good fun?
Um, we all said that we were glad we were in a band and that we weren't experiencing it as a solo artist, because I think the isolation of it would have been very difficult at that time. Now we're all rather more used to isolation, but then sort of being shut in a room and not really being able to go out much. The sadness for me was missing all the places we were traveling to, because literally we were prisoners
Mm.
in the hotels, and usually we got banned by the hotels too, because you can imagine the other guests weren't terribly keen on 1,000 fans outside all night singing. Yeah, I mean, it really became problematic, and security was difficult because there was always fans trying to get room keys, and you'd be surprised how clever some of them really were.
Yeah.
But it was, I mean, I suppose my strangest memory from that was being in a limo, one of those big old Goodfellas 1980s American limos, and our car just literally got covered in fans, and it was like being under attack by an alien species. There was no way out. We were all inside the car, and they were all over it, and the sound became more muffled apart from screaming,
Oh my God.
and the driver was panicking and wanted to move forward, and we were all shouting at the driver saying, no, 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 you can't move. We don't anybody to be injured. You have to stay. So the longer we stayed, the more and more. So you can imagine this swarm around us just grew to hundreds and hundreds of people, and we couldn't move, but we couldn't tell anyone. There was no mobile phones or anything then. So we were just stuck there. And that memory has always remained, because actually all I could see were faces pressed up against the glass. And I was thinking, I hope the glass doesn't break, and I hope nobody gets injured. It did all, it ended fine, but when the police came, but it was really out of a horror movie.
I can imagine. I think it's fair to describe you as one of the main architects of 1980s synth pop, which over the last 15 or 20 years has enjoyed a real renaissance. And did you see that coming when that started coming up in the early aughts?
uh, no, I mean, I think what goes around comes around with
Hmm.
music, with fashion, with art. There are styles that tend to repeat. When we were first making music in the early 80s, there were a lot of new synthesizers and samplers coming out, and technology was changing. Studio gear, harmonizers, effects pedals were all different. And I think that it was the use of those things within sound that gave the 80s part of what is familiar to people. I mean, as it happens, I tried to avoid most of the sounds that everybody else used because I thought it would date very, very quickly if everything started to sound the same. I still feel that about music now. When I hear music on the radio that all sounds the same, I'm looking for the one that doesn't sound the same. But technology is really what a lot of that was.
Yeah.
And so now people, I don't know, people like The Weeknd, I guess, who I like very much. I think he's a very clever songwriter and performer. It's very much 80s styled.
Sure. And so, I mean, you're talking about the technology, a lot of these synthesizers, the Jupiter 8, Moog, these things that you helped make famous, and that they ceased producing them. They've now begun manufacturing them once again. What's it like playing a reissue of a synthesizer that you kind of had cut your teeth on its original form?
Well, the Jupiter 8, I've got 3 of the original ones, which is what I use all the time. I do still use Roland Gear, who are the people that made a lot of the equipment I've used throughout my career, because I think they are pretty much the best at what they do. Moog also I use, who are great. But the newer synthesizers are different. A lot of stuff is really just done in the computer now. And people use soft synths, and you have to go through loads of parameters and digital things. I'm a little more impatient than that. I like to be able to do things live, and so I like to turn a knob or push a button and have a physical reaction from it rather than clicking on things.
Sure.
So I'm not a big fan of soft synths, but having said that, many of the records that you hear every day, whether you like it or not, are made purely in a computer. And it's filled with extraordinary sounds now. Anything that was a digital sound sounds the same. It's just, 8-bit or 16-bit or 32-bit, whatever. But Roland's, they still make great synths. Actually, both Brian and I have one in common. We have one called the Phantom, which was I think their flagship new digital synth, which is part analog too, that came out last year.
And I want to hear about how your relationship to old and new synthesizers factors into this latest project, Astronomia. Could you first just give us an overview of the project? Tell us about it.
Yeah. I was working with a wonderful artist called Wendy Bevan, who is a performance artist, singer, songwriter. And I was introduced to her by a mutual friend, and we got chatting away. She's just got great taste in everything she does. And I thought, actually, let's spend a day in the studio together, see what happens. She wanted someone to write with and to produce her new solo album. So we started making these atmospheric instrumental tracks, and we didn't really know what they were. And then about 10 instrumentals in, it started to remind me of space and the skies and stars and astronomy. And so we based the pieces on that. And then my OCD kicked in, and I said, okay, so we want 52 pieces of music. I want 13 on each album. That's one for each week. And we're going to release them on the solstices and the equinoxes throughout the year.
And the first track that came out, The Great Attractor, it's beautiful. And I love the accompanying images that you have. I mean, it's both ambient, orally and visually. And is that song, The Great Attractor, about gravity?
Yeah. I mean, we say it's instrumental, but each of the titles sort of inform the piece of music, or we listen to the piece of music and then I searched around in space for the right mood for what we're creating. And, for example, the second album, which was recently released, The Rise of Lyra, that one is all based around that constellation.
Okay.
And we try to draw in things that inspire the songs more. We use mythology too, for sure. I have a a deep admiration for Jean Cocteau, and he used mythology a lot within his work. Well, most famously, apart from all the beautiful drawings and paintings, he made the Orphée trilogy about Orpheus. And they are three extraordinary, surreal, abstract movies that hold up beautifully well for anyone who hasn't seen them. And I always go back to those for inspiration.
We're talking about, constellations, gravity, planetary motion, and these are all phenomena of science that, we can appreciate with the naked eye. And Brian, I want to ask you, as a particle physicist, how could you introduce us to what is happening on a invisible subatomic scale?
Science is, as Nick has alluded to, science is the study of nature at all scales, from the smallest building blocks of the universe, which I should add, we don't know what they are yet. The smallest ones we've discovered, all the way up to the large scale structure of the universe. And very little of it we can perceive directly. So we don't only have to focus on small things, subatomic particles. We have no direct experience of black holes, for example, which is some of the most massive and violent objects in the universe. We really have no direct interaction as human beings with the galaxy. I mean, you can just about see the Andromeda galaxy, which is our nearest large galaxy, with the naked eye, just about. But I don't know whether I suppose the ancients did notice it, but they wouldn't have been able to make it out. We didn't know it was a galaxy until the end of the 1920s. So I suppose science is, it begins with what you can see directly and very simple questions. Why is the sky blue? Why is grass green? And so on. Why do things fall to the earth? Which is a very good question. When you talk about gravity, the Greeks would have said things fall to the earth because it's at the center of the universe. It's the thing that all things fall towards, which is entirely logical. So in some ways, I suppose science is about, one definition of it is it's about stripping away your preconceptions to try and to get to a deeper understanding of how things work. The answer to your question is, I don't think it matters whether they're the smallest things or the biggest things, because we can see neither.
Mm-hmm. But as I understand it, the laws of physics become altogether different when you start talking about the smallest building blocks of matter.
Well, yeah, I mean, I suppose you're alluding to quantum mechanics, but actually the laws of nature are what they are, right? And our current view, by the way, is that everything is quantum mechanics. So what is quantum mechanics for your listeners? It's nothing strange or weird. It's about how particles move around and how they interact with each other. And it was developed in the 1920s primarily, you could say a little bit before, because there were certain things that our model, which was a very Newtonian model. So think of a particle, you tend to think of it as a little speck or a little marble or something, and they tend to bounce off each other. And that may be our, the way that many of us would think about the small building blocks of matter. But it turned out that picture of the way that matter behaves is not right. It doesn't describe what we see. In particular, it couldn't describe something very simple, which is the colours that emerge when you burn things, like sodium burns yellow very famously. So the colours that atoms emit when you heat gases up. Couldn't explain it. Couldn't explain the way that hot things behave. So there were a lot of observations at the turn of the 20th century which led us to a rather more counterintuitive description of nature. And that's all it is. And now we think that all nature behaves in that counterintuitive way. It's just that the very big things that we experience in everyday life kind of obscure that strange behavior. I'll give you one example of how counterintuitive it is. If let's say you think of an electron, which is the smallest particle, one of the smallest particles we know of, the particle of electricity. And you say, well, what is it? How does it behave? Is it a little speck? So I can put an electron somewhere and it just stays there. Is that the way it behaves? Well, the answer is no, it doesn't behave like that. In some sense, it fills the room, fills the box in which you try to contain it. So it behaves in some ways like an extended wavy object. But in other ways, it does behave like a little thing that bounces around, like a little point-like object. And actually, I know before we were talking, before we started recording, you were saying about one of the purposes of this podcast is to speak about not only music and science, but also its relation to politics and society, the way that we think, the way that we behave. And it reminds me of there's a wonderful series of lectures which you can get online by Robert Oppenheimer, who's probably best known as the father of the atom bomb, the Manhattan Project. But actually, before that, he was a very famous physicist, worked on black holes, actually, some of the really early work on black holes. But he did the Reith lectures, the BBC Reith lectures in 1953, and you can get them online as PDFs. You can't actually get all the audio recordings because they were deleted. Okay. Can you believe it? You had to save tape or something, taped over. But you can get the transcripts. And in there, he addresses the question of what thinking scientifically can teach us. So is there a transferable skill, let's put it that way, that you can take from science, the way that nature forces you to think, and transfer that into politics or the wider society? And he used the electron and quantum mechanics as an example, because he said, the thing is that there are two ways of looking at the electron, as I said. There's this point-like thing that moves around, or in certain circumstances, it's better to think of it as a wavy, extended thing that kind of interferes like waves on water and so on. And he said, so nature forces you to think like that. Neither of those are correct. Neither of them are the absolute truth about an electron. An electron is some combination, a so-called linear combination of the two. So you can only characterize it by shining these different lights on it, thinking about it in different ways. And Oppenheimer said, so it is with society. So in a human society, there are tensions, the rights of the individual, the needs of the individual. You might call that an extreme, a kind of libertarian view of society. And at the other extreme, and remember, Oppenheimer had all sorts of trouble with McCarthy and things. So he spoke about the collective, the needs of the collective. He would say, well, communism is the extreme version of that way of thinking. But you know what he meant, right? You could translate it to modern language, needs of the individual, needs of society. And he said that if your politics leans heavily or exclusively to one or the other, you are disadvantaging yourself in your way of thinking in the same way that you would be disadvantaged if you thought of an electron as a point-like object or an extended thing, because it's neither and both at the same time. You need both pictures. You have to develop the skill of holding them both in your head at the same time in order to get a deep understanding and a full picture of nature. So it is with society, he said. And it's very wise, actually, because in our polarized times, it's quite natural, you see it on social media all over the place, for people to say, well, I'm one thing or the other thing, and I go with these people. This is 100% right, this is 100% wrong. Oppenheimer, of course, was right. Nature teaches us that there's no such thing as being 100% right and 100% wrong. They're just a mixture. And it's how you weight the different ideas. In physics, we call them basis vectors, right? But it doesn't matter what they are. They're kind of like axes. It's like, I'll finish in a minute. It's like, if you imagine in a room, you have a point, a position in a room, and you could set up three axes and say, well, it's along by 3 feet and across by 9 feet and up in the air by 12 feet or whatever it is, right? So that's three different numbers you can describe this point using. But of course, there are lots of other ways of doing it. You can tilt those things around. You could describe it as angles instead of distances and so on. And so that's what the point Oppenheimer was making. It's human societies are very complicated. Nature's very complicated. And therefore, you have to hold lots of different ideas in your head in order to get a full description of it.
It's interesting. It's about open-mindedness, though, isn't it, really, Brian? Because I think with politics, it's very easy to become polarized, and people are either left or they're right, or they're this party or that party. But in reality, if you really find intelligent politicians, which I know is somewhat of an oxymoron, but there are some somewhere, I'm sure. If you do find somebody who's got a proper view about a specific subject or something culturally, often those views can be surprising, whichever party they're from. And it's very, in America particularly, I think there's so little happens across the aisle anymore that's really disappointing, because one would hope there was a gigantic grey area in the middle where people that were intelligent and like-minded could actually find things that they can agree on, aside from pulling the party politics line. And I think that's always been the problem with many things in life, and with science for sure. I'm sure Brian can explain much better than I can. But all the people that really made the big discoveries were the people that were completely open-minded and who believed there was maybe a way to find out something that other people thought wasn't true or was impossible.
Yeah, Richard Feynman, another great hero of mine, contemporary of Oppenheimer, actually also worked on the Manhattan Project. Also, not coincidentally, in the 1950s, spent a lot of time thinking about politics and science and the interaction of science and knowledge with the wider society. And he defined science as a satisfactory philosophy of ignorance, which is a beautiful definition. Satisfactory philosophy of ignorance. It is fundamentally based on the idea that we do not know. And Feynman actually said that it's the open channel, he called it. It's a beautiful phrase. The open channel to wisdom is the understanding that you don't know how to do it. And he said that's actually the foundation of democracy, if you think about it. What is democracy? What is changing government every 4 years, other than the acceptance that you don't know how to run a country? If you think you know how to run a country and nobody else does and you're right, you're not a democrat, because then you don't accept the fact that somebody else needs to have a go in a few years' time. And he's absolutely right. A satisfactory philosophy of ignorance. I mean, Oppenheimer expanded that. He said, if you think about it, because we've all, I don't know, whatever, people who are listening will have different politics. Sometimes politics goes our way, sometimes it doesn't. And you've seen that in the States, you see it in the UK, controversial things like Brexit and so on. Sometimes things go your way, sometimes they don't. Oppenheimer said that you should think of that as a pendulum. Because we don't know how to do it, because it's too complicated, there are different views on how to run society. So sometimes the pendulum will swing one way, sometimes it will swing the other. First of all, the fact that it swings at all tells you that you live in a free society. So actually, and he said this swing of a pendulum, it's the manifestation of and the guarantor of your freedom. Right? It's the manifestation of it because it says that things aren't going my way. Not everybody agrees with me. Fine, I live in a free society. If everyone agreed with me, it wouldn't be a free society. And the fact that it swings tells us that the satisfactory philosophy of ignorance is accepted. And so we try different ways of doing things. And it's hard, right? I'm sure all of us think, well, God, the world's going in the wrong direction. But sometimes it'll go in the right direction as well. If it carries on going in one direction, that's when you should worry about it.
Well, I wish more of our politicians thought less like attorneys and more like scientists, in the tradition of Feynman and Oppenheimer.
Yeah, the interesting thing about the timing of their interventions, right, in the 50s, is that they both seen what the Manhattan Project did. And they both say that they were surprised in some sense that they were still there. They were still alive in the 50s because they felt that they delivered knowledge to civilization, to politicians, to the human race, that the human race was not wise enough to deploy.
No, they're not wrong.
Oppenheimer once quoted that famous quote, "I am become death, the destroyer of worlds." Right? So it's that he noticed, or he was very preoccupied actually by the fact that absolute knowledge and the quest for absolute knowledge is dangerous. And obviously it was made, manifested in the atom bomb. But just in general, this idea that we know it all is a dangerous idea. I could read actually. Coincidentally, I wasn't going to talk about this, but I've actually sat here with, and I've got Feynman's book in front of me. And there's this beautiful, the essay, by the way, you can also get online if you're listening. It's called The Value of Science. You type in The Value of Science, Richard Feynman, you'll get it online. And he says this at the end of his essay. He says, "It is our responsibility as scientists, knowing the great progress which comes from a satisfactory philosophy of ignorance, the great progress which is the fruit of freedom of thought, to proclaim the value of this freedom, to teach how doubt is not to be feared but welcomed and discussed, and to demand this freedom as our duty to all coming generations." That's right, isn't it? He's actually
Yeah, I mean, one of the first episodes we did on the show was Nora Jones' Don't Know Why with a science activist who was talking about the importance of embracing uncertainty. You mentioned something in your description of the electron that I have a real hard time getting my head around. And this applies to, I think, all particles, that you observe them only by shining a light on it. Is that what you said?
The thing about quantum mechanics is that it's a strange theory because there are interpretations of it. Mm-hmm. So you don't really have interpretations of Newton's law of gravitation, right? It is what it is. But quantum mechanics has got this strange feature. It's in two parts, really. There's the way that you describe, given an electron in some state, we call it, at some point. So we know everything about the electron. What's that state going to be at some point in the future? And quantum mechanics is perfectly able to allow you to calculate that absolutely precisely as you want. But there's also an additional bit in quantum mechanics, which is that if you say, well, where is it then, the electron? Now, or how fast is it traveling? Or you ask a direct question, then the theory then becomes probabilistic. So what it says, it doesn't give you an answer. It doesn't say it is here. It was there at 1 minute, so it'll be here the next. What it says is, if it was like this at one time, then there's a 25% chance it'll be in this region in a minute, and there's 30% chance it'll be in that region, and so on. So it's a theory of probabilities. And that leads to what you're alluding to, which is these kind of interpretations of what the theory means. Because obviously, if you actually do observe the thing and you go find it, then when you found it, then it is there. It's where you found it. And then it will float off and distribute itself around again. But in the theory, an idea of observation and what that actually means is not fully agreed upon. So I should emphasize, it's always worth emphasizing when you talk about quantum mechanics. It's not some weird kind of mystical thing. It's a well-defined, very accurate physical theory. What it actually means about the underlying reality, right? What it's telling you about reality is open to interpretation. And that's interesting philosophically in scientific theories. That's an interesting point. It's like, what are we doing? Are we building models of the universe which allow us to calculate things that we can then test? Or are we somehow describing the underlying reality itself, the nature of underlying reality? So in quantum mechanics, you can take the view that you're just calculating. Feynman once famously said, I think it's not actually Feynman, it's often attributed to him, and it was shut up and calculate. I think it wasn't actually Feynman who said it now, but that's a school of physics, shut up and calculate, right? Calculate the thing you want to, quantum mechanics underpins the way an iPhone works. So it does work. So calculate away. Don't ask the question, what does it mean for reality? Because our theories are not concerned with reality. They're concerned with calculating stuff.
How does it underpin the way an iPhone works?
Well, because transistors are inherently quantum devices. You can't understand what a transistor is without quantum mechanics or how it works. So quantum mechanics is a theory that it's the framework within which we understand pretty much everything that we take for granted today, certainly in terms of modern electronics. So it's not, it's not it's a 100-year-old well-tested theory, but it has this, ultimately I think it comes down to the fact that it predicts probabilities. And then it's, what do you mean by that is the question. Okay.
This elusive Higgs boson particle, what's known as, I think regrettably to physicists, as the God particle. It's gotten so much press. What can you tell us about that?
That title, by the way, that came from a book by Leon Lederman, one of the great physicists, Nobel Prize winner. And I think it was just his publisher who thought it was a good title for a book about the Higgs.
Oh, yeah.
And I'm not sure he ever liked it, but he probably did, because it meant he sold a lot of books. It's a great title. No, the Higgs, it plays a very specific role in our picture of the way nature works, which is that it gives mass to the fundamental particles. So what do I mean by that? So an electron, let's say, is a particle that has mass, right? It has substance, if you like. there was a big problem in the 1960s in particular with our mathematical model of particles. That if you had a clumsy way of just writing the masses into the equations, we say the mass of the electron is this and the mass of the quarks is this, and so all the fundamental particles, give them the masses that you measure, then the mathematics didn't work. The theoretical structure sort of crumbled. And so Peter Higgs and others back in the 60s came up with a way of giving masses to particles and preserving the elegant structure of the mathematics. And it's a pretty simple idea. It's that there's this thing in the universe which is the Higgs field. You could imagine Higgs bosons, these Higgs particles. So imagine the universe is filled with this Higgs field. And some particles interact with it strongly, and some particles interact with it weakly, and some don't interact with it at all. And it's that interaction that gives particles mass. So mass is not a fundamental property in that sense of things. It comes from the interaction with the Higgs field. And that solved the technical problems that people had in the 60s. The important thing, the interesting thing to point out is that it was mathematical problems. So this is an example of what the physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the physical sciences. Because it turned out, of course, that 50 years later, a lifetime later, some people, some physicists built the most complex machine ever built, 27 kilometers in circumference beneath the surface of Geneva, switched it on, collided particles together at 99.999999% the speed of light, recreating the conditions that were present a billionth of a second after the Big Bang, and discovered that the thing was Peter Higgs was right, and this thing does actually exist.
Have you been to CERN?
Yeah, well, I work there, so yeah.
Oh.
So that's why it's one of my workplaces. So I was quite heavily involved initially in the LHC and some experiments there when it was under construction.
Brian, I remember you telling me about CERN that they needed so much computing power that they basically had to build their own internet to store all the information that was coming out, because it was churning out such vast amounts.
Yeah,
right?
I mean the internet. Well, not the internet, but the World Wide Web is a CERN invention, famously, Tim Berners-Lee, and that was in the late 80s, and it came from the fact that particle physics requires, as you say, there's loads of data and there's loads of people all over the world collaborating to work on that data. So it requires that you can collaborate over long distances on big data sets. And that's essentially what the World Wide Web is for initially. And that's why it was invented by Tim Berners-Lee at CERN for a particular purpose, really, which is collaboration across the world. And that's what CERN is. So, yeah.
So it got the name the God particle because it's what gives matter mass. Is that the idea?
Yeah, well, it got the name, as I said, the God particle, because the publisher thought it was a good idea to sell a book. But yes, it gives fundamental particles mass. So as such, it's one of the most important components of our understanding of nature. Because if nothing had mass, then there wouldn't be structures in the way that we know them. We certainly wouldn't exist. You wouldn't get stars and planets and galaxies. So it's a fundamental part. It's necessary for structure in the universe, by which I mean us. Right? We're structures in nature. It is clearly fundamental. We don't fully understand it. There's no doubt about that. We've discovered these things, these Higgs bosons. CERN now is acting in some ways like a Higgs factory. So now what we're doing at LHC is making lots of Higgs particles so we can see exactly how they behave. Because it's certainly true the theory is not complete. Our picture of the universe is not complete. So in that sense, it's a misleading idea. It wasn't the answer to everything. I suppose God isn't the answer to everything, right?
It's a very dark matter.
Yeah. Hello.
Yeah, no, that's good.
Wait, what's the difference between a Higgs field and dark matter?
So dark matter is something else entirely. If you look out into the universe, then at every scale, whether you look at the way galaxies rotate or galaxies interact, or you look at our models of the way that galaxies formed in the early universe, you always see multiple different observations that you need more matter in the universe than we can see. So we see stuff like stars shining, gas in the galaxies that glows. And so we can count up, we can measure how much matter we can see in the universe. And we can also measure how much matter there is there by looking at its gravitational interaction, right? So how much gravity does it make, basically? And there is more gravity there, put it that way, than can be accounted for by the stuff we can see by a large factor. It's about a factor of 5. So what we think probably is the case is that there's some other kind of subatomic particle that we've yet to discover, which dominates the universe and which doesn't interact very strongly with the stuff out of which we are made. So in particular, it doesn't interact with light. So if something doesn't interact with light, you can't see it.
Mm-hmm. Right.
Basically. So that's why it's called dark matter.
Okay. And what are the fundamental subatomic particles?
Well, at the moment, we have 12 matter particles and the Higgs and 4 forces of nature. So 12 matter particles, just the very brief 1-minute lecture, is that you and me and everything we can see are made of essentially 4 particles. Up quarks and down quarks, which make up protons and neutrons, which make up the atomic nucleus. Electrons, which go around the nucleus to make up atoms, molecules, and so on. And then a particle called the neutrino, which is quite unfamiliar, but there are billions of them passing through your head now from the sun. So they're released in nuclear reactions in the sun, for example. And that's pretty much all you need to make the universe that we see. So 4 of them. For some reason, nobody understands. There are 2... I used to call them carbon copies, but if I say that in a school now, no one knows what you're talking about. So 2 other families of particles, which are identical in every way, except they're more massive. And we don't have any idea why nature chose to have 3 copies of the fundamental particles. You know, it seems like you only need 1, but there are 3. Don't know why. So that's 12 matter particles. The Higgs particle, the Higgs boson. And then there are 4 forces of nature, of which the most familiar one is electricity and magnetism, so electromagnetism, gravity, and then two things called the weak and strong nuclear forces. And that's it. Okay. So that's the full set as far as we can tell. However, as I said, we strongly suspect there's something else, which we're calling dark matter, but we haven't discovered yet.
I'm not surprised they made copies. I mean, every time I take a photograph, I put it on a drive, and then I make at least 2 other copies because I know something's going to go wrong. So,
you know, what I'm working on at the moment is black holes. And very briefly, black holes are the collision. There are 2 pictures, right, of the way the universe works. There's the subatomic particles we've talked about, and then there's gravity, which is rather different in description at the moment. And these 2 descriptions collide in black holes. But the reason I thought of it, what Nick said, is because we're beginning to focus now on information and how information underpins the way the universe works. And in particular, how information goes into black holes and then comes out again in the far future in what's called Hawking radiation. So black holes evaporate over long periods of time. And that's caused lots of wonderful problems in fundamental physics. But we're beginning to understand how the information seems to be encoded in the radiation that comes out of a black hole. And it's intimately related with the structure of space and time themselves. But the thing that Nick said, which is interesting, is it seems that coding is redundant. There's a redundancy built into it. So there is a sense in which the universe works with an information backup. Right, nature seems to work with the backup, which is entirely sensible, as Nick said, if you think about it. But it does, you know. Then you're faced with the question: well, how did it get to that? How can space and time be built in such a way that there's some kind of information backup built into them? And of course, the answer is we don't know.
So this brings me to another question. I don't know how much sci-fi either of you read, but it seems that black holes and quantum mechanics become this catch-all for fantastic phenomena, be it time travel, immortality. Is that baloney in your estimation, or are all things possible with black holes and quantum physics?
The thing about black holes, what I can say is they're telling us that space and time, which are those most fundamental human things. And we should talk in a minute, actually, about how music and the arts helps you try to think about those issues. You know, you don't find meaning in science, right? You don't find meaning through the end of a telescope. Science can show you a framework, the framework within which we live, but it doesn't tell you what it means and how you're to interpret it. But with space and time, the study of black holes is telling us that they're not fundamental. So I think that's widely accepted now. So this idea there's something deeply hidden in nature. And the thing that's deeply hidden, the deep structure of nature, seems to be inside a black hole, right? In some metaphorical sense. By studying them, we get a glimpse into something deeply hidden.
And we have no direct experience interacting with a black hole.
No, I mean, we've got an image of one now, taken by a network of radio telescopes.
That was only last year, wasn't it?
Yeah. So
last year or the year before?
It was about 18 months ago, wasn't it? Yeah. And it's a remarkable image of this thing, 6 billion times the mass of the sun. Imagine that. 6 billion times the mass of the sun, about 50 million light years away in the heart of a galaxy called M87.
Funny, isn't it? It looks so tiny in the picture, Brian.
Yeah.
Well, it kind of is tiny. It's about twice the size of a solar system, which is actually quite small for something that's 6 billion times the mass of the star at the centre. So it's not that big. It's quite remarkable.
That's a tricky one to get your head around.
In black holes, Einstein really, they're strongly suggested by his theory, and he, I think it's fair to say, never accepted that they should exist. He called them absurd. He didn't think such absurd things should exist. But I was going to say, actually, Nick, because with your latest project, I always say that whatever the central meaning of it all is, right, the central shape of nature and existence, whatever that is, what science and art and music and literature does is it shines different lights on it. It shines different lights on this central thing, whatever you want to call it. And we have access to the shadows. So science is one light that casts one shadow. Music is another light that casts another shadow. And I'm sure that we can't build up a complete picture of what it means to be human without shining all these different lights onto it. And I wonder what you think of that. I think it's very important, actually, that it goes to the heart of this ancient two cultures debate, which is now old hat, with the idea that science and art and music are different things. I think they're all human pursuits chasing after the same questions.
Me too. Well, it's all about curiosity and creation to me, and living. So when I was a little kid, at first I wanted to be a magician because I just loved that these magic tricks, something happened that I couldn't explain, and things could just disappear out of nowhere. And I wanted to be a part of that world. And then I saw the first moon landing when I was very young. And like every other kid at school, I wanted to be an astronaut because that seemed to be the most fantastical, extraordinary experience you could have, it being otherworldly. And it just looked like the future. They were living the future. And a few years later, I discovered David Bowie. Not specifically with the song Space Oddity, more Starman, which was his first sort of big hit from the Ziggy Stardust album. And when I saw him on Top of the Pops, the British TV show, I wanted to be like that. But I think my thought process as a little kid from the age of about 7 or 8 to 10, 11 was exactly the same. I was attracted to things that I didn't understand, things I wanted to explore, and things that were different, things that were far away, things that were magical, mystical, and creative. And I still think of all of those as interlocking. As Brian said, as a musician, all I'm ever trying to do is put out my own ideas. All the music I make is like my personal diary, if you like. But what I'm trying to do also is attract readers to that diary, or people that are interested in whatever it is I've done. And you try to do that by touching somebody's nerves, by touching their emotions. Music's a very emotional force. I can't tell you why I can stand there listening to, I don't know, Beethoven's Fifth, and I might start crying at some point. I don't know why. It just hits something that affects you And it really, I've always found that about music that I love. And the same thing with art that I love. If I'm standing in front of a painting or a sculpture or even an installation, it needs to connect with me. When I go to an art gallery, I actually can walk around quite quickly past a lot of things, but suddenly I'll get stopped in my tracks. Something will attract my attention. And I think that it's the same for music. It's what are you attracted to? I mean, for me, it was always David Bowie and Lou Reed and Roxy Music and things like that when I was growing up, and Kraftwerk and Giorgio Moroder. But now I probably find myself listening to more classical music. Things change all the time in life, but I really do feel that we're all on the pursuit for the same thing. We all like discovery. We all like to find something that we relate to. And if you don't relate to the universe and to science and to nature and to looking up at the sky, and if you don't have awe and wonder at what on earth all of that is and what it means, then I don't know, you're missing an awful lot in life.
Yeah, I was thinking, I think that cosmology in particular is terrifying, isn't it? There's awe and wonder, there's also terror. I mean, it's terrifying. The fact that there are, 2 trillion galaxies at last estimate in the observable universe. Yeah, 400 billion stars in our galaxy. I know a lot of people who get terrified about that and the fact that we're very fragile and tiny and transient.
Is it possible for it ever to meet a capacity, Brian, where eventually it can't go further? How does science look at that?
No, as far as we can tell at the moment, the universe is going to continue to expand forever. And it could well be infinite. Right. So we may well live in an infinite, eternal universe. And so then I suppose there's no limit to there's a limit, a very fundamental and to some people troubling limit, which is if nothing else happens, nothing that we don't understand other than this continuing expansion, then you do get to a point where there are no stars anymore. Stars have a finite lifetime, and partly because stuff gets locked inside black holes. So all the material in a star doesn't necessarily get returned into the universe to make new stars. So in any given region of space, the number of stars that are made falling in the Milky Way at the moment. The maximum star formation rates were many billions of years ago. So galaxies die. So the universe, as far as we can tell, dies ultimately. And so the age of starlight, if you want to call it that, is finite. And there will be a last star, as far as we can tell, which bothers people. I should say it's a long time. It's something like, I think it's something like 10 trillion years. We can put a number on it. It's about 10 trillion years, which is a long time. So we don't need to worry.
In the other direction, what does science tell us about what was here before the Big Bang?
Well, it comes down to semantics sometimes. This is what you define as the Big Bang. So we know that there was a time 13.8 billion years ago when the universe was very hot and very dense and very smooth. So not like it is today, filled with hot gas, hydrogen and helium primarily. So we know that because we've measured it. So if people argue with that, you say, well, you can't. It's like arguing with the measurement with the distance between LA and New York. You're not allowed to argue about how far that is, right? So we've got a measurement. It's 13.8 billion years to the Big Bang. However, we do have good reason to think the universe existed before that time. So it was not hot and dense. There's a time before when it was cold and empty in some sense, but expanding very quickly. And that period is called inflation. And that theory has been around for some time. It makes predictions about things like the distribution of galaxies that we measure in the sky, and it made correct predictions. So it's quite a powerful theory. It's a textbook theory. So we think there's something before the universe got hot and dense. Some people don't agree with that, but it's pretty textbook. How long the universe was in existence for before our hot Big Bang, and what it was doing, and whether there's what a friend of mine, Carlos Frank, called the mother of all Big Bangs somewhere where everything began, or whether indeed the universe could be eternal and didn't have a beginning in time, we really don't know. So this is cutting edge cosmology. But I think there's a good reason to believe there was something before everything was very hot.
Food for thought.
Fascinating.
Yeah.
So, Brian, I mean, the question that we all want the answer to is, do you think that time travel is ever going to be possible?
Well, it's possible into the future, which is in some sense a ridiculous thing to say because we're all going to the future at 1 second per second, right? But it's also very important to say that we go into the future at different rates depending on how we move around relative to each other. So time travel into the future in the science fiction sense is absolutely possible. So you could now, if you had access to a fast enough rocket, get into one, fly, go on a trip around Alpha Centauri or something like that, the nearest star, and come back again. And depending on how fast you travelled, you accelerate away from the Earth and then come back, then you would find that you appeared back on the Earth in the far future, according to the people on Earth. And so that can be 5 minutes, 10 years, 1,000,000 years, 10 billion years, right? Depending on how fast you go around in your rocket ship. So each of us can travel into the future relative to everybody else at different rates, depending, as long as we can travel quite fast. So that's clear.
I suppose in a way it's the same as what you used to be able to do on Concorde, because you could leave the UK on Concorde, but because it was only a 3.5-hour flight and there's a 5-hour time difference, I could get to New York before I'd left London.
No, it's different to that though, because it's what it is it's literally, you could experience, let's say you experience 1 year on your spaceship. So you come back and you are a year older. You could come back and I could be 50 years older. So it is literal time travel in that sense. What we don't think is possible, although it's not proven, but we're pretty certain, is time travel into the past. So that the structure of space and time as we understand it prevents you from getting into the past, but it does not prevent you at all from getting into the future at any rate you want.
But if you've gone into the future and you said you return, aren't you then going into the past from the future? Isn't that the Back to the Future premise?
No, you just appear. You would appear on Earth 50 years, and 50 years would have passed on Earth, and 1 year would have passed for you.
So is there a corresponding speed to that? Like if you say...
Yeah, I have one in my head because I know that at LHC at CERN, the protons go around the ring at 99.99999% the speed of light. Okay. 99.999999, right? And at that speed, time passes 7,000 times more slowly for the protons than it does for the experimenters watching them go around.
Christ.
So if you could go in your rocket at 99.999999% speed of light and then come back again to the Earth, so if you could do some sort of loop around at that speed, then 1 year for you would be 7,000 years for Earth. I should say into the past, if you can build things like wormholes, which is another bit of science fiction, which are allowed in Einstein's theory in the sense that you can draw them, you can describe the structure of space and time that you would call a wormhole, right? It fits in the theory. Then you can travel into the past. Which causes all sorts of trouble. But what seems to be the case is that you can't make those things in nature. So Stephen Hawking wrote a paper once called a chronology protection conjecture, in which he conjectured that the laws of nature will be such that you can't do things like build wormholes that you can travel through. But it's not proven.
Did you spend much time with Stephen Hawking? I mean, no, you were fellows.
Yeah, I met him several times. The most bizarre was I was asked by Eric Idle at Monty Python if I knew him, and I said, yeah, I do know Stephen. And so he said, well, can you email him and ask him if he's a fan, and would he take part in a sketch? So I emailed Stephen, and the reply came back very quickly, which was, yes, I'm a huge Python fan. I will do it. Yeah, and so we went to see him in Cambridge, and Eric had got an idea. There's a song called the Galaxy Song, and I'd always said to Eric for years, we've had this kind of running joke that it's just not right. It's all this stuff about the Earth going around at 8,000, whatever it is. All the numbers that are used in the Galaxy Song are now wrong, right? So the whole thing is atrocious. And he keeps saying it's the trouble with you scientists. You keep changing your mind, right? You keep measuring new things. And so we got this ongoing joke for years that the Galaxy song is all wrong. So the idea was I would, after the Galaxy song was performed at Python Live at the O2 in London when they did the live shows, I would come on and say, well, this is all nonsense. It's atrocious that children can listen to these lyrics because it's so incorrect that it's just irresponsible. And as I was saying that, the idea was Stephen would come in his wheelchair and come flying along the side of a river in Cambridge, knock me to the ground and say, I think you're being pedantic. And then he starts singing the Galaxy song. So we did it. So you can watch it online. So he's there. And it was one of those Python-esque moments where I remember looking at Eric and we were in Stephen's office and talking to him and telling him this joke, and he was laughing and talking about it. And we said, this is ridiculous. One of the great physicists of the 20th and 21st century, which he is. Right? He is one of the greats of recent years. And to just sit there talking about a comedy sketch where he knocks me over in his wheelchair and starts singing is the most grotesque misuse of time that you could ever imagine. But that's what we did. So, yeah.
That is so cool. Yeah. And I really appreciate your giving the time to do this because I know you're both so busy.
Well, it's a real pleasure. I mean, it's... I should say, actually, I saw Nick the other day when we were talking about music, and then I discovered that joy of discovering new music, that, just something you've not heard, and how it can just knock you over, as Nick said, you walk through an art gallery. I just, for some reason, had never listened to Keith Jarrett playing Somewhere Over the Rainbow on the La Scala album. And I'd never listened to it for some reason. It came up on one of those things I was listening, and it just suggested it, and I listened to it. And I was so blown away by it that I sent it to Nick straight away. And Nick sent me a text back going, yeah. And Nick had this great line. He said that he's like a musical archaeologist, Keith Jarrett, because he just he finds something in songs that you don't think.
So under the surface,
so
wasn't it? Yeah. Oh, it was great, that, actually. I really enjoyed that. It was a good find, Brian. I'm not very familiar with a lot of his work either, but it's really beautiful, exquisite.
It is. And then someone else the other day, I was saying this, and they said, have you heard him play Danny Boy? So there's a version he did, and it's the same. It's this utter mastery of harmony, and chord substitution, just not vulgar, not showing up, just absolutely beautifully melodic. And so there are always new things to discover.
Is the Keith Jarrett trademark moaning audible throughout?
Yeah. Although I think he's quite quiet on Over the Rainbow because he's not, going full on 100 miles an hour kind of thing.
I've got to show that to my daughter. I just introduced her to the Muppet movie the other day.
Rainbow Connection, one of the great songs.
Oh, you said Over the Rainbow. Right.
That's a great song, though. Rainbow Connection.
Good. Yeah, you see my mind's on frogs and pigs. Anyway, again, thank you both so much. This has been tremendous.
Pleasure. It was fun.
Be sure to check out Duran Duran's brand new album, Future Past, and Nick's project with Wendy Bevan, Astronomia. Professor Brian Cox is on tour in 2022 with his new show Horizons, a 21st century space odyssey, with dates in the US and across the world. Visit briancoxlive.co.uk for more info. Special thanks to Ashley Winton, Will Wood, Noah Murphy, and Melissa Kaplan for their help with today's episode. Sing for Science is co-produced by Talkhouse and brought to you with support from Science Sandbox, an initiative of the Simons Foundation. Our music is by Panoram, media by Otavio Media and Bailey Constas, and press by TCB Public Relations. Please be sure to subscribe to Sing for Science on your podcast platform of choice and follow us on Instagram, Twitter, and Facebook @Sing for Science. Thanks for listening.